Welcome to Spring LIB.
In this question, we are going to explore the interference pattern of white light on a thick layer of water on top of glass in order to learn why is it that only thin films will produce, some pretty rainbow colors with their interference. So one of the key things I like to start with is a quick sketch of our situation, just indicating that we have a layer of air, and then we're going to have this thick layer of water, labeled thick as T, and then we're going to have a layer of glass. And we're asked first to show that a visible color will be reflected from the water layer if its wavelength is lambda equals 2nt divided by m, where m is an integer. So we need visible colors to constructively interfere. And we are going to have a phase shift of half a wavelength at the air-water interface because we're moving from a lower index of refraction into a higher index of refraction. So we'll pick up a half wavelength here, and then similarly, because the index of refraction of glass is going to be greater than that of water, we are going to have another phase shift here. So what this tells us is we need the path through the glass to be an integer number of wavelengths to maintain the construct of interference. So the fact that we have both reflected rays getting a phase shift means they're going to emerge. The second one's going to emerge in phase and all automatically constructively interfering with the one reflected from the top layer. So the path through glass is an integer number of wavelengths. And this now lets us set up the fact that 2t, because we're going to go down and then back up, equals m times our wavelength within the film. Well, our wavelength within the film is equal to the incident wavelength, or wavelength in a vacuum, divided by n. So that lets us say now that 2t equals m lambda over n. And now we can rearrange to say that lambda is going to be 2n t over m, as we were asked to show. And now show that the two extremes of wavelengths for visible light, 400 nanometers and 700 nanometers, are both reflected from the water layer. Ooh, fun. So what this means is for our red wavelength of 700 nanometers, let's calculate m for it. So all I did was multiply both sides of that equation by m and divide by lambda so that we have 2nt divided by lambda r in this case. So we have 2 times our index of refraction of 1.33. We were given a thickness of 200 micrometers, so 200 times 10 to the minus 6 meters. And then we have to express our wavelength in meters as well, so it's 700 times 10 to the minus 9th meters, and I get a value of 760. So there will be 760 of these red wavelengths that fit in the thickness of the glass. Well, let's do the same thing for, oops, I meant to grab another color. Hold on. All right, and so now we're going to do the same thing for the blue end, 400 nanometers. Oh, it would have been smart if I had written the red one in red, but it's okay. we don't have to color code. So M for our blue color is going to be 2nt over lambda blue. So we'll still have 2 times 1.33 times 200 times 10 to the minus 6 meters for the thickness of the film, divided by now 400 times 10 to the minus 9th meters for our light, and I get 1,330 wavelengths. And then we're asked, how many other visible wavelengths are reflected from the thick layer of water? I'm actually going to type this answer. So let's make this nice and big so you can see it. And we'll do it in green. How about that? So, oh, it didn't give me green. There we go. Let's do it in green. Yes. There we go. So, every single other value of M between 760 and 1330 will correspond to a wavelength that gets reflected. So that's 569. So if you get the difference between them, it's 570, but we've already counted one of them. So, 760 up to 1329, and then we count 1330 is the very next one. So that's 569 more wavelengths that will reflect. All right, and then how does this explain why such a thick layer does not reflect colorfully but is white or gray? Well, again, we are just going to go ahead and type this one as well. And purple, because that'll be fun. So somehow we got changed to not size 18. There we go. So with so many wavelengths being reflected, across the visible spectrum, our eyes naturally perceive this as white or gray. Because notice that our wavelengths won't all be integer numbers of wavelengths. There will be decimal values as well. But every single possible wavelength that has that integer value of M is going to be reflected. And that's 570 wavelengths out of a difference from 400 to 700 nanometers. That's like twice as many wavelengths as the integer values of those wavelengths. So of course, we're reflecting so much of the light off of a thick film that it looks white or gray instead.